Hello and welcome to the third episode of IT for Non-Techie. Today we are going to talk about an important component of backend development, which is databases. So today we will discover the different types of databases. You will understand what does it mean SQL and NoSQL database, what does it mean replication, what does it mean scalability, and the different security options for database. As always, don't forget to like the video, share it with your friends if you want to, and subscribe to the channel. And I'll let you watch the video and enjoy your learning. Imagine running a small library with hundreds of books. You need to track their titles, authors, and availability. Managing this with paper and random notes will be chaotic. That's where a database comes in. It organizes and manages information so you can easily store, find, and update data. A database structures information efficiently, often using tables with rows and columns. Similar to what? Similar to spreadsheets in Excel. This setup makes searching, sorting, and updating records quick and accurate. For example, in a banking system, a database ensures that your account balance updates correctly after each transaction. Databases allow users to search for specific data, finding a book in the library, update the records when someone brings back the book, you will make it as available, delete outdated information if someone breaks the book so it's no longer available, you need to remove it, and add new entries. You have a new book arrived, so you need to make them available in the database. There are two main types of databases. Relational databases, this is the SQL database. It stores data in structured tables and uses SQL, structured query language, to manage it. It's ideal for customer records, inventory tracking, and financial data. NoSQL database is more flexible, handling various types of data, making them great for social media, real-time analytics, and big data application. In short, databases are essential for keeping information organized and accessible, whether tracking books, processing transactions, or managing website users. They make data management faster, easier, and more secure. Now that we understand what a database is, let's talk how it is managed. A database by itself is a just structured collection of data, but how do we interact with it efficiently? That's where Database Management System comes in, DBMS. DBMS is software that acts as a bridge between users, applications, and the database itself. Instead of manually handling data, the DBMS provides tools to create, maintain, and access databases in an organized and secure way. It ensures that data remain consistent, protected, and available whenever needed. Whether it's a banking system handling thousands of transactions or an e-commerce platform processing orders, a DBMS keeps everything running smoothly. To understand its importance, let's look at the key functions of a DBMS. First, it handles data storage and retrieval, ensuring that information is stored efficiently and can be retrieved quickly when needed. Users can easily query the database to find specific records without having to search manually. Next, it supports data manipulation, allowing users to perform essential operations known as CRUD: create, read, update, and delete. This means data can be added, viewed, modified, or removed effortlessly, keeping the database up to date. Security is another crucial aspect. A DBMS provides data security by implementing authentication and authorization mechanism. This ensures that only authorized users can access or modify sensitive information, protecting it from unauthorized changes or breaches. In addition, a DBMS includes backup and recovery features to safeguard data. In case of system failure or accidental deletion, these mechanisms allow data to be restored, preventing permanent loss. Finally, it manages concurrency control, which is essential when multiple users access the database at the same time. Without proper control, simultaneous changes could lead to conflicts or inconsistencies. A DBMS ensures that transactions occur smoothly without interfering with each other. As we said, there is two different types of databases. First, we will start with the relational database, the SQL database. Relational databases are one of the most widely used ways to store and manage structured data. They organize information in tables with rows and columns, making retrieval and management efficient and reliable. Instead of keeping everything in one large file, relational databases link related data across multiple tables, reducing redundancy and improving consistency. These databases are managed using structured query language, which allows users to retrieve, modify, and manipulate data easily. Key characteristics of relational database. Information is stored in clearly defined tables, making searching and filtering fast and efficient. Relational between tables. Data is connected using primary keys, it's a unique identifier for records, and foreign keys, links to records in another table, ensuring organization and consistency. Asset compliance. Transactions follow atomicity, consistency, isolation, and durability, meaning data remains accurate and reliable even in case of failure. Schema-based structure. A predefined schema sets the format for storing and linking data, ensuring clarity and organization. I know, these characteristics are not that clear. We need to go a bit in depth, right? And that's what we will do now. Now we're gonna focus on the first principle, which is the structured data. This is what makes relational databases highly organized and efficient for storing and retrieving information. In a relational database, data is stored in a tabular format, meaning it is arranged into rows and columns, much like the spreadsheets. Each column represents a specific attribute or characteristic of the data. For example, in an employee database, columns might include name, age, and salary, defining the type of information stored in each field. On the other hand, each row represents a single record or entry in the table. A row contains the actual data for one entity, such as an individual employee, with their corresponding details filled into each column. This structured format makes it easy to search, filter, and update records efficiently using SQL queries. To maintain accuracy and uniqueness, databases often include a unique identifier for each record. In an employee table, this could be an ID column, ensuring that every employee is distinctly recognized, even if other details like the name, for example, are similar. This approach not only enhances data consistency, but also simplifies data retrieval and management. In a relational database, data is not stored in isolation. Instead, different tables are linked together to create meaningful connections. This is where relationships between tables come into play. To establish these relationships, relational databases use primary keys and foreign keys. A primary key is a unique identifier for each row in a table, ensuring that no two records have the same value in this field. For example, in an employee table, the employee ID could serve as the primary key, uniquely identifying each individual. A foreign key, on the other hand, is a field in one table that references a primary key in another table. This creates a connection between related records. For instance, if there is a department table where each department has a unique department ID, an employee table can include a department ID as a foreign key to indicate which department an employee belongs to. By enforcing these relationships, the database maintains data integrity and prevents inconsistency. This structure, known as referential integrity, ensures that linked records remain valid. For example, an employee cannot be assigned a department that does not exist. Imagine you are using a bank application and you sent money to your friend. The money left your account but never reached your friend's account. This is a huge problem. Let's discover together a principle that a database should adhere to make sure that the data stay consistent and all the transactions are processed in a good way. ACID stands for atomicity, consistency, isolation, and durability, which are 4 key properties that help maintain data integrity and stability, even in cases of system failure or simultaneous operations. Atomicity ensures that a transaction is treated as a single and divisible unit. This means that either all parts of the transaction are successfully completed or none of them are executed at all. For example, when transferring money between two bank accounts, both the debit from one account and the credit to another must occur together. If one part of the transaction fails, the entire process is rolled back to prevent inconsistencies. Next, consistency ensures that the database remains in a valid state before and after the transaction. Every change must adhere to a predefined rules and constraint, preventing errors and corruption. If a transaction violates these constraints, the system automatically rolls back. For instance, if a database enforces a rule that prevents duplicate user emails, that means, for example, you want to create a new account using already used email. Attempting to insert a duplicate will trigger an error, ensuring that data remains correct and organized. Isolation is another critical property, guaranteeing that multiple transactions can execute independently without interfering with each other. This prevents one transaction from accessing incomplete or uncommitted changes made by another. For example, if two users attempt to update the same record at the same time, the database ensures that their changes do not conflict, maintaining data accuracy. Finally, durability ensures that once a transaction is committed, it is permanently stored even if the system crashes. This prevents data loss and guarantees that completed transactions remain intact. For example, if a customer places an online order and the system crashes afterward, the order details remain safely stored in the database and do not disappear. By adhering to these ACID principles, relational databases provide a stable and secure environment for managing data. These properties are essential for applications that require high accuracy and reliability, such as financial systems, healthcare records, and enterprise databases. A key characteristic of relational databases is that they are schema-based, meaning they require a predefined structure before storing data. A schema acts as the blueprint that defines how tables are organized, including the number of columns, the type of data each column can hold, and the relationships between tables. This structured approach ensures that data remains organized and easy to manage. One major benefit of schema enforcement is that it maintains data integrity and prevents inconsistencies. Since every table follows a strict format, errors such as missing or incorrectly formatted data are minimized. For instance, if a column is designed for dates, the database will reject any attempt to insert text into that field, ensuring that data remains accurate and structured. However, because relational databases rely on the predefined schema, modifying the structure requires careful planning. Adding a new column or changing data types or altering relationships can impact existing records and applications that rely on the database. This is why schema changes often involve database administrators or developers who ensure that updates are handled without disrupting the system. Relational databases offer a structured, reliable, and efficient way to store and manage data. Their schema-based design ensures that data is well organized, while relationships between tables link information seamlessly using primary and foreign keys. By enforcing ACID compliance, relational databases maintain integrity, prevent errors, and ensure smooth transaction even in complex multi-user environments. The use of structured data in a tabular format makes it easy to store, retrieve, and manipulate records using SQL. While schema enforcement guarantees consistency and accuracy, although modifying the schema requires careful planning, it ultimately helps create a stable and scalable data system that businesses and organizations can rely on. You know how traditional relational databases store data into those neat, structured tables, like everything has to fit perfectly into rows and columns? Well, not all data plays by those rules. That's where NoSQL Database comes in, offering a much flexible way to handle data that doesn't fit into needy or predefined box. Instead of sticking to rigid tables, NoSQL Database organizes data in format like documents, key value pairs, graphs, or time series structure. This setup makes it easier and faster to pull up information, especially when the data is unstructured or constantly changing. One of the biggest perks of NoSQL is scalability. Since there is no fixed structure to follow, these databases can handle massive amounts of data and easily adapt as your needs evolve. That's why they are the go-to for things like social media platforms, real-time analytics, and big data application. One major difference between relational and NoSQL databases is how they handle schemas. In relational databases, every table has a fixed structure, meaning any change requires modifying the schema. In contrast, NoSQL databases have a flexible schema allowing data to be stored and adapted without strict rules. For example, in document-based NoSQL databases, each record can have different fields depending on the available data. For example, one record might include name, age, and address, while another in the same collection may only have name and email. Unlike the relational databases, there is no need to update the schema to accommodate these differences. This flexibility is especially useful for user-generated content, real-time analytics, and application with varying data format. Since NoSQL databases adapt easily to changing data needs, they provide a scalable and efficient solution for modern application. So we said that NoSQL databases allow data to be stored in different formats depending on the application needs. This flexibility makes them perfect for handling unstructured or semi-structured data. Now, NoSQL databases come in 4 main types, each designed for a specific use case. Now we're gonna introduce those 4 types in a general manner, and then we're gonna talk about them more in details later on. Let's start with document-based databases. Think of these as digital file folders where data is stored in JSON documents. A great example for this kind of database is MongoDB. These databases are ideal for user profile, product catalogs, and hierarchical data, where each entry might have a different field. Second, we have the key value stores. These are the simplest NoSQL databases. Imagine a locker system. You have a key and a value inside. Databases like Redis or DynamoDB work this way, making them perfect for caching and real-time lookups where speed is very important. And then we have the column family stores. So instead of storing data in rows, these databases organize it in columns, which speeds up large-scale analytics and big data storage. Examples include Cassandra and HBase, often used in applications that process a huge amount of data. Finally, we have the graph databases. These are designed for highly connected data. Instead of tables, they use nodes and relationships, making them great for social networks, recommendation engines, and fraud detection. In distributed databases, keeping data consistent across multiple servers can be challenging. And like relational database, which enforce strong consistency using the ACID transactions, many NoSQL databases follow an eventual consistency model. This means data updates may not be immediate, but will sync over time across different nodes. The key difference is how updates are processed. Relational databases ensure immediate consistency, meaning all users see the latest data instantly. However, this can slow down performance, especially in large-scale systems. NoSQL database prioritizes speed and availability, allowing update to propagate asynchronously across multiple servers. A common example is online shopping systems, where a customer buys a product, the inventory updates across different locations, but some servers may take a moment to reflect the change. This trade-off keeps the system fast and always available, even if some updates are still processing. Developers choose between eventual consistency and strong consistency based on the application needs. Eventual consistency works best for high-speed, scalable systems, while strong consistency is crucial for banking, medical records, or other real-time applications where accuracy is critical. Modern applications generate huge amounts of data every second, from social media posts to IoT sensor readings and e-commerce transactions. Managing and analyzing this data quickly is crucial, and NoSQL databases are built for this kind of challenge.
And like traditional databases, which can struggle with rapid data growth, NoSQL databases scale easily and process large datasets efficiently. Their flexible structure allows for fast data ingestion, retrieval, and analysis, making them perfect for real-time applications. For example, in an IoT system, NoSQL databases continuously collect and analyze sensor data from millions of devices, ensuring critical information is always available. A great example is social media platforms like Facebook, which process billions of posts, comments, and messages daily. NoSQL database store and retrieve this data efficiently, keeping performance smooth even during high traffic. With high-speed performance, scalability, and real-time processing, NoSQL database help businesses make faster decisions, enhance user experience, and manage massive amounts of data efficiently across different industries. To summarize what we've seen, we can say that NoSQL database offer flexible, scalable, and high-performance alternative to traditional relational database. And like relational database that require a fixed schema, NoSQL database allow for schema-less storage, making them ideal to handle unstructured and semi-structured data. Now let's discover the different types of NoSQL database. Let's start with document-oriented database. Document-oriented database store data in flexible document instead of rigid tables. Think of it like digital filing system. One customer profile may have just one name and email, while another may include the address, phone number, purchase history, and so on. Each document can have its own format, unlike traditional databases that require a fixed structure. These databases use JSON, BSON, or XML, making data easy to read and update. They are fast and efficient because they store related data together, reducing the need for complex joins. This speeds up data retrieval, making them ideal for e-commerce, content management systems, and real-time analytics. A big advantage of document database is a quick search using indexing, even with large amounts of data. MongoDB is a popular example, known for its scalability and flexibility. Business use these databases for blogs, online stores, and dashboards as they can handle changing data structure without issues. Now you may ask, what is this indexing? So indexing helps database find data faster. So instead of scanning every document, an index works like a table of contents in a book. You go straight to the section you need instead of flipping through every page. For example, e-commerce sites searching for a product with laptop in the name instantly finds results using an index instead of scanning the entire product database. Indexes, they boost performance, especially in large databases, making search faster and more efficient. Now we will move to key value stores. Think of a key value store like a gym locker. You get a locker number, that's the key, and you place your belongings inside. That's the value. When you need your stuff, you don't check every locker, you just go directly to your number, and that's exactly how the key value store works. Since data is accessed directly by its key, lookups are incredibly fast. Instead of scanning an entire database, you call the key and the data appears instantly. This makes key value stores perfect for applications that need quick access like caching. For example, when you visit a website, some data like your logging session or frequently visited pages is stored in a key value database. The next time you visit, the site loads faster because it retrieves the data instantly instead of searching through everything. Key value stores are also great for real-time applications like stock market tracking, gaming leaderboards, and live chat systems. Since they fetch and update data almost instantly, they help applications respond in real time. One of the most popular key value database is Redis. It's widely used for caching, session management, and real-time messaging. For example, websites use Redis to store user sessions, so you don't have to log in again every time you refresh a page. Now we're gonna talk about the column family stores. Column family stores are a powerful way to store and analyze large amounts of data efficiently. Unlike traditional databases that store data in rows, these databases organize information in columns, making it faster to retrieve specific data. Think of it like a spreadsheet, but instead of searching row by row, you can pull up an entire column instantly. This structure is especially useful for big data application and distributed systems that handles massive amounts of information. One major advantage of column family stores is flexibility. Unlike relational databases that require fixed structure, each row can have a different column. This prevents wasted storage and allows the data structure to evolve over time. It's ideal for managing logs, sensor readings, and user profiles where data formats change frequently. Performance is another key benefit. These databases are built for fast reading and writing, allowing them to process a huge dataset efficiently. They spread data across multiple nodes, making them highly scalable and fault tolerant. This is why they are commonly used in real-time analytics and big data processing. Finally, we have the graph databases. Graph databases are designed to handle highly connected data, something like traditional databases struggle with. So instead of using tables, they store data as nodes and edges, making it easy to see relationships between different pieces of information. Think of it like a mind map. Nodes represent things like people, products, or locations, and edges show connections such as friendships, purchases, or travel history. This setup allows for faster and more efficient relationship analysis compared to traditional databases. One of the biggest advantages of graph databases is their speed when handling complex relationships. In relational databases, finding connection require multiple joins, which slow things down, but graph databases use graph traversal, allowing them to quickly explore relationships without extra processing. This makes them ideal for social networks, fraud detection, and recommendation engine, where connections between data points are just as important as the data itself. They also handle hierarchical and interconnected data naturally, making them useful for company hierarchies, supply chains, and knowledge graphs. Since relationships are built into data models, searching for connected information is fast and efficient even with large datasets. Now, how we can choose the right NoSQL database? The right NoSQL database depends on what your application needs. Some prioritize flexibility, others focus on speed, and some are designed for handling relationships between data. Choosing the right type helps ensure better performance and scalability. Document-oriented databases. If your data structure is flexible and constantly changing, MongoDB is a great choice. It stores data in documents instead of fixed tables, making it perfect for content management systems, CMS, e-commerce platforms, and real-time analytics. For fast data retrieval, Redis and DynamoDB are ideal. They store data as simple key-value pairs, which make them great for caching, managing user sessions, and handling real-time events. Column family stores. If you need to process large data sets efficiently, Apache Cassandra is a strong option. It organizes data in columns instead of rows, making it perfect for big data recommendation engines and time series databases. Graph databases. For applications that rely on complex relationships like social networks, fraud detection, or recommendation engines, Neo4j and Amazon Neptunes are the best fit. They store data as nodes and connections, making it easy to find relationships quickly. In today's world, databases need to handle large amounts of data while staying fast, reliable, and always available. As businesses grow and demands increase, databases must be able to recover from failure, scale efficiently, and continue running without interruptions. That's a lot to do. To achieve this, modern databases use backup, replication, and scalability techniques. Backups create copies of data to protect against loss, ensuring information can be restored if something goes wrong. Replications improve availability by keeping multiple copies of data across different locations. This reduces downtime and increases system reliability. Scalability is also crucial. Databases handle increasing workloads using two main strategies: horizontal scaling, which is sharding, and it spreads data across multiple servers to balance the load, while vertical scaling boosts a single server's performance by adding more CPU. These strategies help databases manage heavy traffic and complex queries efficiently. Modern databases also follow the CAP theorem, which describes the trade-offs between consistency, availability, and partition tolerance. Some databases focus on strong consistency, ensuring all copies of data are always the same. Others prioritize high availability, allowing operation to continue even if some nodes fail. Data is one of the most valuable assets for any organization, and keeping it safe and protected is a top priority. Without a proper backup and recovery strategy, businesses risk losing important information due to system crashes, cyber threats, or accidental deletion. Losing data can lead to downtime, financial loss, and major disruption in operations. To prevent this, organizations must have a strong recovery mechanism in place. A good backup strategy creates copies of important data at regular intervals, ensuring that lost information can be restored quickly. These backups can be stored on local servers, cloud storage, or off-site locations, making sure that data remains secure and accessible even if the main system fails. Beyond the backups, having a disaster recovery plan is just as important. This plan outlines the steps needed to restore systems after a failure, minimizing downtime and keeping operations running smoothly. To keep data safe and easily recoverable, organizations use snapshots and automated backups as key parts of their backup strategy. These methods help protect important data and allow for quick restoration in case of corruption, system failure, or accidental deletion. A snapshot is like a frozen image of a database at a specific moment. If something goes wrong, the system can revert to that snapshot, minimizing downtime and preventing data loss. This is especially useful for high availability systems that needs fast recovery to stay operational. Alongside snapshots, automated backups ensure that recent copies of data are always available. These backups run on a schedule, so businesses don't have to manually save their data, reducing the risk of human error and keeping information up to date. To make backups more efficient and cost-effective, many systems use incremental backups, which only save changes made since the last backup. This speeds up the backup process and reduces storage costs, allowing frequent backups without overloading system resources. For applications that need to be available all the time, replication is a key technique that helps keep data safe and accessible. Imagine using a banking app or an online store. If the system goes down, it could cause serious problems. Replication prevents this by creating multiple copies of a database and storing them in different locations. If one copy becomes unavailable, another copy can take over instantly, ensuring that everything keeps running smoothly. What is replication and why it is important? Replication means duplicating data across different servers. If one server fails or crashes, the system can switch to another copy without interrupting the service. This is especially important for banks, healthcare systems, e-commerce sites, and other online services that people rely on all the time. Without replication, a system failure could lead to lost data, downtime, and frustrated users. There are two different types of replication: synchronous and asynchronous. Synchronous replication ensures that every data change is copied to multiple locations instantly before completing the transaction. This guarantees that all database copies stay identical at all times. It is great for financial transactions and medical records where accuracy is extremely important. However, because it waits for confirmation from all copies before saving data, it can sometimes be slower than other methods. Asynchronous replication copies data over time instead of instantly. This makes the system faster because it doesn't wait for all copies to update before processing new data. However, some copies might be slightly behind the latest changes. This method is useful for applications where speed is more important than immediate accuracy, such as social media updates, online content delivery, and data logs. Now let's talk about the multi-region replication. Many businesses use multi-region replication to store database copies in different locations around the world. This helps in two ways. It's faster access for users, like people in different countries can retrieve data from the closest server, and this is reduce the loading times. And also, it's a protection against outage. If a server in one region goes down due to a power failure or cyber attack or whatever, the system can automatically switch to another region. Failover. Another important feature of replication is failover, which acts like a backup plan if the main database fails. Failover automatically switches users to a backup copy, preventing downtime. Think of it like having a backup generator for electricity. If the power goes out, the generator kicks in immediately, keeping the lights on without you noticing. In the same way, failover ensures that applications keep running even if something goes wrong. Recovering from accidental deletions, system failure, or cyber attacks is a critical part of managing a database. Losing important data can disrupt operations and cause major problems, but point-in-time recovery offers a powerful solution. PITR allows database to rewind to a specific moment in time, restoring them to a state before the issue occurred. This ensures that even unexpected data loss can be quickly undone, keeping business operations running smoothly. How PITR works and why it is different. Unlike a full database restore, which rolls the entire system back to the last saved backup, PITR logs all changes over time. This means instead of losing all recent updates, administrators can restore the database to an exact moment, keeping valid changes while removing only the problem. This is especially useful when data is accidentally deleted and needs to be restored without affecting new information. Data corruptions occurs and only the corrupted transactions need to be removed. A security breach happens and you need to roll back to the moment before an authorized access. By pinpointing the exact recovery time, PITR provides flexibility and minimizes data loss. Many cloud databases providers now include point-in-time recovery as a built-in feature. Some examples like MongoDB Atlas, Amazon DynamoDB, PostgreSQL on cloud platforms. Ensuring data availability, reliability, and a quick recovery is essential for modern database systems. Various strategies like the snapshot, automated backups, and replication help safeguard critical information and prevent data loss due to failover, cyber attacks, or accidental deletions. Replication plays a key role in high availability and fault tolerance, maintaining multiple copies of data across different locations. As businesses grow and data volume increases, databases must handle large workloads without slowing down. This is where scalability matters. A scalable database adapts to a higher traffic. Databases scale in two ways: vertical scaling, which is upgrading a single server, or horizontal scaling, spreading data across multiple machines. The choice depends on performance needs, cost, and system complexity. A good scaling strategy ensures fast queries and efficient resource use, supporting everything from e-commerce to real-time analytics. With the right approach, businesses can keep their systems fast and reliable as data grows. Scaling a database means making it bigger and faster to handle more users and data. There are two main ways to do this. Vertical scaling, which means scaling up, this means making a single computer more powerful by adding more memory, the RAM, or better processor, means CPU, or more storage. It's like upgrading your phone to a faster model, for example. This works well for small databases, but there is a limit to how much you can upgrade. And sometimes the system needs to be turned off during the upgrade, which is not very nice. Horizontal scaling, scaling out. Instead of making one computer stronger, this method adds more computers to share the workload. It's like having multiple cashiers at a busy store instead of just one. A technique called sharding splits the data into smaller parts and spreads it across different computers so no single machine gets overloaded. When to use each one? Vertical scaling is simpler but has limits. Horizontal scaling is better for huge websites and apps like social media or online stores because it keeps things running smoothly even with millions of users. Modern applications don't always have the same amount of traffic. Sometimes they are busy and other times they are not. To keep databases running smoothly, two smart scaling methods are used: elastic scaling and distributed scaling. Elastic scaling grows and shrinks as needed. We can say that elastic scaling lets a database automatically add more computers when traffic is high and remove them when traffic is low. This way, businesses only use and pay for the resources they need. It's like a food delivery service, hiring more drivers during rush hours and reducing staff when it's quiet. Distributed scaling, which means spread the load. So instead of depending on one computer, distributed databases store data across many computers. If one fails, another one takes over, so the system keeps working without interruptions. This is great for apps that need to be available all the time, like global websites or online banking. Load balancing, keeping things fast. To avoid overloading one computer, load balancing spreads incoming requests evenly across multiple machines. To summarize what we saw already, as businesses grow, databases need to scale efficiently to handle more data and users without slowing down. This can be done through vertical scaling, which is enhancing a single server, horizontal scaling, which means adding servers to share the load, with advanced techniques like elastic scaling, distributed scaling, and load balancing, ensuring better performance, reliability, and cost savings. Now let's move to CAP theorem. When databases are spread across multiple locations, distributed database, keeping everything perfectly updated, always available, and resistant to network failure at the same time is impossible. The CAP theorem explains this by saying a system can only guarantee 2 out of 3. First, we have consistency. Everyone sees the same up-to-date data, needed for things like banking, where numbers must be correct. Availability, the system is always working even if some parts fail. Important for online shopping, where customers should always have access to the products. Partition tolerance, the system still runs even if parts of it lose connections. Used in social media, where small delays don't break the system. Since database can't have all three together, it must prioritize two. First, you have consistency and partition tolerance. This keeps data accurate but may have delays. We can use this in banking. Availability and partition tolerance. It stays online, but data may be updated slowly. We can use it in social media or shopping sites. Consistency and availability works in smaller single location systems but struggle in big and global networks. We've seen the different types of databases. While each has its own strengths in performance scalability, they all face security risks. This includes unauthorized access, data breaches, injection attacks, insider threats, and denial of service (DOS) attacks. If a database is not well protected, businesses could suffer financial losses, reputational damage, and legal issues. To prevent these threats, database security relies on strong authentication, access control, encryption, and monitoring. Techniques like SQL injection prevention, auditing, and real-time threat detection help keep systems safe from attacks. In this session, we'll explore how these security measures work across different databases and how they protect data from cyber threats. By the end, you will understand how to keep databases secure and maintain a strong defense against evolving risks. Keeping a database secure starts with controlling who gets in and what they can do. This is managed through two key security measures, authentication and authorization. Together, they ensure only the right people have access and that their actions are limited to what's necessary. Authentication verifies a user's identity before allowing them to access the database. Traditionally, this is done with a username and passwords, but modern systems add extra layers of security like multi-factor authentication, MFA, biometric scans, or single sign-on, SSO. These methods help block unauthorized users and protect sensitive information. Once a user is authenticated, authorization determines what they can do inside the database. Not everyone needs a full access. Some may only need to view data, while others may require permission to edit, delete, or manage settings. Role-based access control, RBAC, ensures users only have the minimal permission needed, reducing the risk of accidental or malicious changes. By combining strong authentication and strict authorization, businesses can protect sensitive data, reduce security risks, and keep database access well regulated. Keeping databases secure means giving users the right level of access, nothing more and nothing less. One of the best ways to do this is through role-based access control, which ensures users only have the permission needed for their jobs. In RBAC, users are assigned roles like admin, developer, or read-only, each with specific permissions such as reading, writing, or deleting data. Instead of assigning permissions to individuals, RBAC groups users by role, making access management easier and reducing security risks. A big advantage of RBAC is that it follows the principle of least privilege, POLP. Users get only the access they need, preventing accidental or malicious actions on sensitive data. As cyber threats increase, protecting sensitive data is more important than ever. Encryption secures information by making it unreadable without a decryption key, ensuring that even if someone gains access, they cannot use the data. One key method is encryption at rest, which protects stored data from theft or breaches. By encrypting files, databases, and backups, businesses ensure data remains secure even if physical storage is compromised. Most modern databases use AES 256 encryptions, a widely trusted standard across SQL, NoSQL, and cloud-based systems. Encrypting stored data is important, but it's just as crucial to protect data while it's being transmitted between users, applications, and databases. This is where encryption in transit comes in, keeping sensitive data secure as it moves across networks. This type of encryption uses SSL, TLS, secure socket layers, and transport layer security, a security protocol that encrypts communication between clients and servers. It prevents man-in-the-middle attacks where hackers try to intercept or alter data during transmission. Without it, information sent over network, especially in the cloud-based applications, could be exposed to cyber threats. Sometimes encrypting data at rest and in transit isn't enough, especially in sensitive industries like banking, healthcare, and finance. Client-side encryption adds an extra layer of security by encrypting data before it even reaches the database, ensuring that even if someone gains unauthorized access, the data remains unreadable without the right decryption keys. This method is widely used to meet strict security regulations like GDPR. By encrypting data at the application level, businesses reduce the risk of exposure from server-side vulnerabilities, keeping information secure throughout the entire lifecycle. To implement client-side encryption, developers use encryption libraries such as libsodium or OpenSSL, which secure data before it is stored. Cloud providers like AWS Key Management Services, AWS KMS, also offer tools and manage encryption keys for both SQL and NoSQL database. Database security isn't just about controlling access and encrypting data. It also requires constant monitoring and auditing to track who accesses, modifies, or deletes information. This helps detect security threats early and prevents data breaches. A key part of auditing is logging user activities, which records who did what, when, and from where. This is not only helps identify unauthorized access, but also provides a record for investigation if a security incident occurs. To be effective, logs must be stored securely and reviewed regularly because attackers often try to delete or alter logs to hide their tracks, so protecting them ensuring accurate records. Regular log analysis help detect unusual activity, enforce security policies, and comply with regulations like GDPR. By monitoring and auditing database activity, businesses can quickly detect threats, strengthen security, and stay compliant, keeping their systems safe from cyber attacks. While authentication, encryption, and auditing help secure database, real-time threat detection is essential for identifying attacks before they cause damage. Intrusion detection systems, ADS, monitor database activity and alert administrator to suspicious behaviors like repeated failed logins or unauthorized queries. Detecting unusual pattern early can prevent cyber threats from escalating. If a user keeps entering the wrong passwords or tries to access restricted data, an ADS can immediately send an alert, helping stop hacking attempts before they even succeed. To strengthen security, businesses use specialized monitoring tools. They use open source solutions like Snort, for example, to analyze network traffic for threats, or cloud security services like AWS GuardDuty or Azure Security Center, which provides an automated monitoring and security recommendations. And secure database need constant monitoring, not just occasional checks. Real-time tracking helps businesses detect issues before they become a major problem, preventing slowdowns, crashes, or security breaches. Monitoring tools provide live insights into database health, helping administrators spot performance issues, resource spikes, and security threats. Open source tools like Grafana, for example, they track query times, CPU usage, and memory consumptions with real-time dashboards. And also we have cloud-based services like AWS CloudWatch or Google Cloud Monitoring to automate monitoring and alert administrator about potential problems. To improve security, setting up alerts for unusual activities is so important. If there are suspicious logins, a surge in database queries, or unauthorized changes, administrators get instant notification to take action.